The Rockies are right over there. Don't just go to the conference. Go and see the Rocky Mountain National Park. Go hiking up at Bear Lake or something. Don't do what I did, which is just to come for the conference. Go and see the area.
So while he tries to get this going here, I'll at least start from somewhere. I'm Jody, and today we're going to be talking about interprocess queues. We're not going to be talking as much about the queues themselves as issues that come up when you try to use queues across processes, because C++ says almost nothing about processes. And as a result, there's just wisdom that you acquire over time. There's things that are defined in the language, there's things that work, there's things that work most of the time, and there's things that work some of the time. I gave a talk similar to this at C++ on C earlier in the year, and in there I go into more detail about how these queues work, how the atomic operations are done. I'm not going to go into that today. Since then, I've actually gotten a few questions and had several discussions, and so what I'm going to do is I'm going to try and talk about things. I will go into those issues and some of the basic issues, like our favorite implicit lifetime stuff. But I will also spend more time on some details of implementation, including how to implement the magic buffer, because I've had a number of questions about that, how you do several other things. So there'll be a lot of code, and hopefully we'll actually be able to see it, because I don't think speaking C++ is probably in the cards for any of us. In the past few years, this is a very close community, and I've had a lot of people asking me about my wife. I've gotten to where I was just give people updates when I speak, because that was kind of an easy thing to do. It was easy because things were going well. A few weeks ago, we had our latest visit to the doctor, and they're not going so well anymore. So I just wanted to at least give you an update. The cancer in her lungs and her liver is pretty much about as active as it was back a year or so ago. And they've run some tests. There's not a whole lot of known treatments that are supposed to be effective for her. So she starts a drug trial on the 25th, next week. So I'm not sure how that's supposed to come over. I don't know. We're very hopeful, and I hope you'll be hopeful as well. But it is the way it is, and I can't just come in and say, hey, she's doing great, and then when she's not, just not say anything at all. But she was supposed to come here this week, but she's not feeling so great, so she stayed home in South Carolina. But when we talk about interprocess queues, there's some things to understand. First, when I talk about message queues, I'm not talking about task queues. I'm not talking about queues, job queues that most of us are familiar with. Like you have a queue and you have some tasks or some jobs, and you'll put them into the queue, and then you'll have a bunch of workers that come along and take the task off out of the queue. They'll execute the task. And if you have 10 or 12 workers and you put 20 things in the queue, those 10 workers, as they get stuff, they'll gobble the first 10 things off. And so each one of them sees the first thing on the queue. And that's what we think of mostly with queues. There's a specific type of queue. That's not what I'm talking about, though.
Password? I just logged on, sorry.
Oh gosh, I can't even see it. Oh, that's not the... There we go. That's right. So I'm talking about message queues, okay, where you actually put a message on a queue to send a message to someone else or to some other part of processing. If you're familiar with actually Alan Kay and the old original idea of object-oriented programming, he claims that object-oriented programming is all about the messages. It's all about the messages that are sent between components. That's what object-oriented programming is about. And the encapsulation of those components so that it's just about passing messages and getting work done. I had a talk in 2022 where I talked about reviving an old design through using a thing called streams. And I was excited about it because now I can implement that in a standpoint at compile time. So when you think about message queues, I want you to think about them from a conceptual point of view. We're going to talk specifically about concrete message queues in shared memory that are being shared across processes. But when we think about message queues, we can think about them from a conceptual point of view. You think of a message queue, it could be a pointer in a register that gets passed to a function call. But if you think about just ideas of I've got some stuff to do and I'm going to pass messages between each component, it really gives you a lot of composability. Gives you a lot of ways to build systems and put them together because you don't care where the next thing is. You're just going to pass a message. The next thing may be a function in my program. The next thing may be a queue to a thread that's running in my process. The next thing may go to a shared memory queue that's read by another process. It may be something that goes to a queue that then gets forwarded across the network to something in Europe. You don't really care. I mean, unless you're concerned about the latency. But as far as from writing your code, it doesn't matter where these things are. So when I talk about message queues, these are the types of queues I'm talking about, where you're putting messages on a queue. Obviously, in my background, I want very low latency message queues. So when I talk about queues between processes, we're going to talk about queues that get mapped into your address space. They're shared from one process to the other. And there are FIFOs. You put a message in, and the first one comes in, the first one comes out. If you've got one consumer, then that consumer will consume those messages. If you have multiple consumers, then every single consumer gets to see every single message. Now, it's hard to go on too much farther without being able to show code or examples, but maybe I'll just turn my computer around. But if you, use, there's something there.
It's not playing it though. It keeps dropping once I play it.
Well, I'll try and see if I can go through. Yeah, let me see what I can do here. Oh, but you know what? Can we get it back to where now? There it goes. You can see something there. Let me see how big I can make this. Yeah, it's a good thing that my talk is code heavy with code samples to show on the screen. Maybe we can act out message queues. I'll just talk about some things that I don't have to show you on here, right? With some code. So there's one problem that we have. If you look at message queues that come about from the internet or things that you might be familiar with, you're probably familiar with single producer, single consumer message queues that are based on atomic counters, right? And so you've got an atomic counter. You've got an atomic counter for the reader and for the writer, and they basically have this buffer. And the write counter is where the writer can start writing bytes. The read counter is where the reader can start reading bytes. And these are atomic counters. And you just move them up, the writer moves it up, writes some bytes. The reader sees where that is, and he can come along and write behind them. These are usually done in big buffers that are like circular queues. I could probably do it without notes, but it's really hard to do it without anything. But if we think about these types of queues, they're okay to use within a process across threads, and we've probably seen them all before. One of the very best talks on this was done a few years ago right here at CppCon. and it was about implementing these single producer, single consumer queues. Talked about all the intricate information. So you'd think that we should be able to go and take Charlie Frash's implementation, or take the Rigtorp implementation, or take the Daugaard implementation, or take any implementation that we've seen, and just be able to take that data structure and put it into shared memory, and put it into shared memory, call mmap on it, or call virtual alloc or whatever, however you're going to share it across your processes, and just shove those things in there. But the problem immediately becomes, what about the pointer to the buffer? Because in two different processes, even though they're pointed to the same memory, they have different address spaces within the processes themselves, because they have their own address space. So they can't share a pointer. So inside your data structure, you're going to be able to have a pointer for the reader and a pointer for the writer. And that's okay. But what you then have to do is you have to make sure that when the writer and the reader come along, that they get the pointer so that they can put data in, and that only they get it. If you think about the API for StudQ, you can push and you can pop, and it has a couple of actually it has 14 constructors. It has a bunch of things. In fact, even though it's a queue, you can actually look at the first element and the last element. Kind of interesting. But what we want to do when we're talking across processes, we don't have the luxury of having code and having a policy that says, hey, this code should only use the push part of the API of that queue, and this code should only use the pop part of the API. The API for StudQ has both of them. You can create the queue, you can add to the queue, you can read from the queue, you can write to the queue. When we're across processes, we have to be much more careful. I'd argue we have to take this amount of care with separation of concerns, even not going across processes. But if you imagine, one process could create the queue, it creates the queue in shared memory. Another process could be the producer, and another process could be the consumer. So why do we want the producer to be able to consume things? And if we have a producer in one process, what's to prevent some other process from just being started up and saying, hey, I want to be the producer too? Well, with normal APIs, there's no checks. I've yet to find an API on the internet. I know they exist in production. I've yet to find one on the internet that actually does anything with this. I wonder how far we can get on here. Change what? The zoom in the top left.
Don't do that.
I'm sorry. Don't do that. Don't do that. Oh, hey. All right. Well, I can't see here, but I'm okay with that. All right. I have no idea where I am in here, but it doesn't really matter. I think we've had a blast. Okay, so yeah, we talked about this. We talked about that. We kind of talked about some of these things. We pretty much talked about a lot of this stuff, and I don't have a whole lot of time left. I doubt they're going to give me I doubt they're going to give me extra time, so I probably need to just run through this stuff. Oh, and you know what? I'm afraid to touch it. I can't see my notes either.
You should be able to now. I can set you up for that.
Is it not going to break?
No. I fixed that. All right. Display.
But when we talk about these, we want to talk about a separation of concerns, right? And we also need to make sure that if it's a single producer, single consumer queue, and a process starts up over here and becomes a producer, that a process over here doesn't also come up and get a producer. Most of this is done in our modern code bases by convention, right? Oh yeah, you're gonna be the producer, you're gonna be consumer. It's undefined behavior if we have more than one of these. It's hard to enforce within a single program. It's almost impossible to enforce if you have multiple processes. So you want to have a separation of concerns where you have at least an object that represents the queue. That's all it represents is the queue. An object that represents the consumer, and an object that represents the producer. The only thing the consumer can do is read stuff off the queue. The only thing the producer can do is write stuff to the queue.
Gotcha.
Thank you.
Yep.
Thank you very much. He's been working on that since 20 till. That's been 45 minutes. He's been very persistent. This is actually a good book here. And in talking about separation of concerns, this is actually a good design book. I recommend it. The first 2 chapters are pretty much full of a lot of ideas, separation concerns, and similar things regarding it. Grab Klaus at the conference. He's here, and talk to him about the book. He'll be very happy to talk to you all night long. But when we talk about these separation of concerns, we want to talk about the queue. The queue is in charge of its construction, its metadata, and its buffer. It's in charge of synchronization. What type of synchronization does the queue itself? It's not a producer or a consumer. Well, it has to synchronize with other people trying to create the queue, right? If you're supposed to create the queue, you should only allow one thing to create it. Well, what happens if 2 programs try to create the queue at the same time? You need to have some type of synchronization there. You have the producer. The producer must have an existing queue. There's 2 general ways of doing this. One is by having the queue have a make producer factory function or something like that, make consumer. Or have the producer take the queue as a parameter to its constructor. Either way, there are pros and cons to each one, but usually one way or the other will fit in with what you're normally usually doing. I prefer to have the queue create the consumer and the producer rather than having you create a producer and pass it a consumer or pass it a queue. I just don't like the idea of passing a bunch of things into constructors. And then we have to observe the Highlander rule. There can be only one, right? If there's supposed to be a single producer, there should only be one producer at any point in time. Trying to create another producer should fail if there's already a producer in existing. And the producer can only write into the queue. The consumer, just like the producer, must have an existing queue. There can be only one in a single consumer scenario. We'll see later where we have multiple consumer scenarios. In that case, there can be more than one. And it can only read from the queue. That's all they can do, okay? I hope this makes sense, and I hope the importance of this gets to you, especially across processes. This has to be enforced by code. It can't be enforced by convention. We'll talk about how we enforce that and some problems that arise. Because if you want to enforce this, you're going to have some problems. Immediately, I'm sure some of you are thinking, if I'm a producer and I grab the lock, whatever the lock is, saying I'm the producer. Sorry, my voice just reminded me when I was 16. If you're going to be a single producer, what happens if the producer crashes? Well, if it shuts down, the destructor runs. And so the destructor should be able to at least release the lock saying it's the producer. But what happens if it crashes? One of the things I passed by in here was that one of the things for me, as far as an interprocess queue, it needs to be recoverable. In other words, if the producer dies, I should be able to start up or have another producer already running that can pick up where it left off on the same queue and be able to pick up where it left off. Well, how do you do it if it dies and it crashed while it was holding the lock? These are issues that we have to solve and we have to at least address in some way. So I consider this not optional. I really do consider that if you're going to write queues across processes and you do not separate these concerns, to me, that's a non-negotiable thing because I've done it the other way. And there is lots of pain there. It is pain that you experience for days, and the trauma lasts for weeks and months and years, decades. Not optional. So there's one thing we could do. We could have an advisory file lock. On most systems today, I'll admit I don't know anything about Windows, so I'm not going to talk about that. Mainly this is about Linux and Mac OS. On most systems, you can represent shared memory with a file. either in like dev shim or dev huge pages or someplace on Linux. In Mac, you can mount a temporary file system that is RAM resident. And so you can do the same thing, represent them with files. You can do this, you can have an advisory file lock. Advisory file locks sound awesome, and there's lots of things in the operating systems in both Linux and Mac OS that provide access to advisory file locks. The problem is that none of them really work, or none of them really work the way that you and I would want them to. So you probably want something like this, which is an advisory file lock class that implements something that allows you to manage these file locks and that automatically makes sure that they're released when it goes away. Inside of your queue, you want to have a set of characteristics that define your queue, make it differentiable from other queues. You probably want to have, in the metadata of the queue itself, some type of signature. This is just some type of maybe even text description of what kind of queue this is. Because you probably will have 3 or 4 or 6 or 10, some number of queue implementations that are designed specifically for the task that you're trying to work with. Single producer, single consumer, MCAS queues, they're not all made the same. They're not all great there's not one of them that's like the best thing for everything. So you'll probably have several different ones. You want to have a signature that will probably represent the kind of queue that's there so that when the producer and the consumer rendezvous, they know my code is built for this type of queue. Let me make sure that that's what I'm looking for. You probably also want to have a UUID. Why? Jody, why are you going to put a UUID in there? That sounds kind of stupid. Well, if you've ever had a program that runs, producer and a consumer, and they rendezvous on a file path because that file path is supposed to be unique, and yet for some reason the clean script didn't clean it correctly, now you have a producer and a consumer that are connected on different queues that don't have the same ID, you can possibly want to get fired, or not want to get fired, but maybe get fired. So having a UUID in here, whenever you have the rendezvous point, right? Somebody creates a queue and they say, hey, here's where you go to find this queue. And by the way, here's the unique identifier of that queue so that when you connect up, you at least have some way of verifying that you're talking to the right thing. Anytime you have processes that are doing lots of things, you've got some type of orchestration or coordination among them. This has nothing to do with the message queue. It has nothing to do with atomics. It has nothing to do with speed. It has nothing to do with fast. It just has to do with trying to make sure that you represent enough data in the queue so that you can connect and make sure that you're not going to have problems later on. How many times are you going to connect to something to the wrong queue? Never, except that one day. I mean, I don't know if you guys have ever been part of something where you can actually say that there was a problem that happened. The problem was isolated. A person interceded, decided to shut the system down. All of this happened in less than 60 seconds, and you still lost millions of dollars. This is something that can happen. And so making sure that these kinds of things don't happen, it's always important. I gave a talk a while back on that talked a lot about what happened with Knight Capital. And it wasn't one error. It wasn't one thing that happened. You take a dozen things that happen. Any one of them, if you say this doesn't happen, most of us never even know that incident occurred. Pay attention to the little things. You have your message size, alignment, cache line size, flags, telling it whether it's single producer, multi-producer, what type of things are allowed. Whether it's an actual inter-process queue, why would you put that in there? I know if it's inter-process because I'm going to find it on the system. Well, you also have queues that are not inter-process, and you might have threads that connect to them. Bugs happen. So these types of things help make sure our systems are robust, which was part of the title, right? Robust inter-process message queues. We have our metadata, which keeps our buffer offset of where our buffer pointer is, our characteristics. It allows us access to our producer lock and our consumer lock. I said earlier that if a producer comes alive and gains, and a producer is constructed, and it is the only producer allowed in the system, there needs to be some way of ensuring that it's the only producer. Well, you can grab a lock, You can grab a mutex, and it can hold that thing. But if it dies, it will not release that mutex. That mutex is sitting in shared memory, or you have some counter or some atomic or something. So what I do here is I have a unique process ID. Now, this is not the PID. The PID is not unique. The PID is small, and it gets reused. The chance of you reusing your PID is pretty small, but it does happen. So this process ID is it's going to be an atomic value, which is why we try to see can we use a 128-bit atomic? Because really what it does is it stores the process ID, the PID T that was given to it by the system, and it stores the time that this process started in as much granularity as possible, hopefully in nanoseconds, because it's unlikely that you're going to recycle through all the PIDs in that amount of time. On Mac, this works for 128. On Linux, it doesn't. Well, that's not true. That's not true. Depends on what system you're on. The Linux machines I use, which are all Intel x86s, they only go up to 64. But theoretically, it's possible that with this type of process ID that you could clash, but it's very unlikely. I mean, the sun will explode tomorrow before that happens. So this process ID is 64-bit. It's expensive to compute, though, because on both Mac and Linux, it has to do some stuff on Linux. It has to like read /dev proc and do some operations and things like that. It's expensive, so we want to cache it. And so here we cache it with an immediately invocable lambda. We store it into the ID. But when I was at C++ on C, I paused right here and somebody said, but what happens if it forks? I was pausing because I was wondering if maybe that would happen again, because that would be really cool. So what does happen if you fork? Well, you're going to have to do something like this. When you do things across processes, you have to think about stuff like this. Because if you're doing cross-process communication, you probably have at least one process in your system that's the orchestrator. It's orchestrating things and forking and execing and probably doing more sophisticated things in order to set up environments for your child processes. So this is an important thing to at least understand. Which brings me to kind of my next point here. Oh yeah, so this ID equals. No, we can set ID equals something because it's static. That address is known. We don't have to capture it. Because pthread at fork only takes function pointers. Pthread at fork, basically, this says, what this code here says is that whenever a fork happens, that first function, prepare, is going to be called before anything else gets done. The parent will be called in the parent after the fork, and the child will be called in the child after the fork. The operating system will guarantee that there will only be one fork happening at a time. And so what we'll do is we'll basically do this. So if you're going to do cross-process communication, you're going to have to at least understand what fork does, what you can and can't do. As shown, you can basically install at-fork handlers. You have to understand that if you're doing process orchestration, anything inside of these handlers or in the child has to be async signal safe. What does that mean? Basically, if you can't write the code in a signal handler, then you can't write it in the child. Technically, there are some things you can get away with because it's not exactly a signal handler, but there's pretty much the same rules. You can call low-level system APIs, no malloc, no printf, no locks, no standard I/O. Most libraries, if they're threaded libraries and they have locks of any kind, you can't do it because whenever you fork, the one thread gets duplicated in the child. All the rest of them, those threads aren't running. So any of those threads that are holding locks, they're holding locks in the child because the child process has the same memory, the same address space layout, and the same objects that the parent did. And so none of those locks get released. So you just have to be careful about this stuff. Unfortunately, mmap is not one of the async signal functions according to POSIX. But anonymous mmap is not POSIX either. I have not been bitten yet doing anonymous mmaps. But technically, you're not supposed to call mmap at all because it's not blessed. I have an at-fork class to register at-fork handlers because at-fork processing can, if you call pthread at-fork, you can register a function. You can't ever remove it. You can't change it. You can't change their priorities. At-fork handling has very specific priorities, and it's based on the order that the at-fork handler was called. A lot of these things get called at static initialization time. A lot of them get called when libraries are initialized. You have no idea which one's going to get called first. So I basically have my own class to install and remove these things and set their own priorities. Prepare always gets called in the reverse order that all the handlers were installed. The child and parent handlers always get called in the order that they were installed. There'll be lots of dragons here. If you ever find yourself thinking, hey, I need to write an at-fork handler for this, you need to think about it again. You probably do if you're doing anything with locks, if you're doing anything with, even if you have your own allocator, if it has any type of lock at all, you're probably going to have to do that because when you fork, it's very possible that some other thread holds the lock and you can't make any progress. What does this have to do with message queues? Nothing. But it has everything to do with processes because if you're doing this stuff, you're going to have to orchestrate across processes. We need to have a lock. So we have this basic lock right here. We've got try lock, which basically calls it simple that we'll look at in a bit. We've got lock here that basically just tries a few times real quick to see if it can get the lock. And if it can't, then it goes into a more waiting policy where you might actually go to sleep waiting for it. When you unlock it, we're just going to do an atomic compare and exchange. This is a little bit safer just because it will only unlock it if you actually hold the lock. You shouldn't be calling it if you don't hold the lock. And if we look at triumphal real quick, we're going to do an atomic exchange with the PID there is the lock. It's the atomic operation that we're contending over. So we're going to do an exchange with our process ID and null, which basically means nobody has the lock. If we're able to do that exchange, then we got the lock and we're done, we're good. If not, then expected will tell us who does hold the lock. It could be me. Maybe some other thread had the lock. If that's the case, I'm just going to return false. If it's me, but if it's not me, then I'm going to go take the PID of this guy that says he owns the lock, and I'm going to get his ID. I'm going to go through that expensive computation of computing his identifier. If I can't get his ID, it means that process doesn't exist anymore. Or if I was able to get the ID and they don't match, it means that the PID got recycled and it doesn't have the exact same start time. And so either case, it means that process is dead and it's gone, and we will rip the lock out of his cold, dead hands. But we can't say that we have it. We have to go back because there could be another process somewhere running on our system that's trying to get that lock too. So we try to see if we can get it. You might go, why doesn't the operating system already have something like this? And if you're on Linux, you do have something like that. It is basically a pthread mutex with the flag of robust. If you use one of these robust mutexes, you can get the same type of behavior out of pthreads. There are some issues with some of this stuff in shared memory. There's some other issues with it, and it doesn't work on Mac, and my stuff has to work on both of those. So this is an interesting way to go about. I have no idea how much time I have left. Not much. So if we look at our producer, we want to be able to write, and this producer is actually the API that hopefully we'll get to later when we see the API for the MCAS queues. So the producer basically can only do one thing. It can just write stuff. Writing can be complicated, right? because you have to prepare a buffer. You have to make sure I get a buffer, as we saw in slides that I didn't present earlier. You have to make sure you've got a buffer that you can write into. And then you put stuff in there, and then once you've written it, you have to mark that you've written it so that the reader knows that it can come and read. We don't want to have to do that stuff over and over again. So we have this one function called write. It takes basically an invocable, and it will pass it a writer that it constructs. And so it'll do whatever it needs to do. It passes you a writer. You can then write stuff. And then when it's done, it does all the magic to make sure that that everything's done. Here's what the writer might look like, or here's what the writer actually does look like for the multicast fast queue, which hopefully we'll get to. You can see here that it basically just has this one has a function to just write a span of bytes. Remember, these are basically, your callback is given one of these writer objects, and then you can write into it safely by calling one of these functions. This one basically does an in place, which allows you to construct in place. It constructs the object, not just does a straight copy. And then this one actually does a write of some number of arbitrary bytes. You can give it an alignment, telling it what type of alignment do you require for this arbitrary set of bytes that you're going to write. All of the locking stuff is taken care of, but these are the types of things that I think are important from an API perspective. The writer can do one thing, it can write. And it can write safely. It has a complicated API. All the stuff in that implementation is trying to do preparing buffers, doing all of this stuff with these atomics. The user has to do nothing about that. The user just says, hey, write this stuff in these various formats. Similarly, a consumer, and this consumer is the same consumer that you would use for one of these multicast queues. It's consuming, and notice that it doesn't get an object of any kind. It just gets opaque bytes. The reason is, look up top. One of the errors you can get is that there's no data. Another error that you can get is that I've been lapped. The reason it's a int64 is because the other type of error you can get is that that's the maximum number of bytes that I could get. Might not be enough, right? But I couldn't get you full. I couldn't get you a full object that you wanted. I'm sorry? These are synchronous calls, yes. Yeah, so the callback that you give it will be executed by the time your function returns. But notice that one there, lapped. Lapped means I'm a consumer and I was too slow. I had my ring buffer. There were 1,000 things in it that I could read. By the time I get back to read it, the system recognizes that I've missed all 1,000 of them. I was too slow and I've been lapped. Well, what am I supposed to do? Crash, recover, be faster next time, make a bigger buffer. There are some recovery strategies, but in general, when these things are used in production, the most common recovery strategy is just to crash. If you recognize you got too slow, just crash. But there are some recovery strategies that we definitely can employ if we recognize that we get lapped. So we're going to look quickly at this Daugaard queue. We looked at it in depth at CppCon, but I also am running way short of time. I hope they give me a little bit more, but who knows. So this will be quick. You can see Casper Daugaard's queue on his website. It has traditional single producer, single consumer things in here. It has an atomic. It has a writer and a reader, where it's going to basically, the writer says, here's where you start writing. The reader says, here's where you start reading. It's got some local state. That local state is for several things. Number one, it's for the buffer. Where are my bytes that I'm having into the system? The second one is this posit in. This is my window that I can write into. Okay, so if the writer has written 100 bytes and there's only 40 left, then this window will be 40, right? This is the window that I can actually, either the reader or the writer can actually use. The next one, base and size, is the size of the whole entire buffer. These windows are kept because you have to make sure, where am I? And this queue does in place construction. So it requires that you have contiguous memory, contiguous aligned memory. And so if it gets to the end and you need 64 bytes and it only has 50, It won't give you the 50 bytes at the end. It will wait until it has 64 bytes at the beginning, and it has to do that computation. There's a way to get past that with the magic buffer, which I do have providing an implementation in here to go through with you. Hopefully we'll get to it. The magic buffer basically allows you to virtually you map two segments of memory over the same actual memory, and so that when you get to the end of the first one, it automatically, even though you're at pointer X, and then you go to pointer X plus 1 byte, the virtual memory subsystem will automatically make that X plus 1 byte point back to the beginning of the buffer again for you. So you don't have to do any of this stuff really at all. But we see that they've got some write commands and some read commands. And actually, the Daugaard implementation, the way that it works, is very, very similar to the way that David Gross describes the FastQ, which is also the FastQ implementation that I was describing earlier, except it has my API on top of it. Because what it's doing is just keeping track of where you are. The only difference is that the Daugaard queue will block if the writer can't get bytes, it will block waiting on the reader to catch up. But if you don't block and you just keep going, and if the reader doesn't block reading, it just reads and has an ability to catch up, the Daugaard queue and the fast queue that David had described are almost identical. But you do have to initialize it because notice it has a couple of things here. You have to give it a reader buffer and you have to give it a writer buffer. So if I took this structure and put it in shared memory, there's two problems, both of them identified on the screen. There's two reasons you can't just use the Daugaard queue. You can't just say, I'm mapping this into shared memory and use it like it is. One of them is very easy to find, very easy to fix. The other one is a little more subtle. Anybody see the first one, the first problem? The pointers, yes. The buffer pointers, both the reader and the writer are both pointing to the actual initialized pointer. It's not really a problem yet because in our implementation, we're going to make sure that there's only one producer ever alive and it's already mapped it. And so what we can do is we can say once the producer has established that he's the producer, he knows where this is, he can go in and adjust the writer pointer to point to the memory in his location. And he can do it safely because there can only ever be one producer. And the same way with the consumer. So they'll update their pointers. So yep, that's the first problem. What's the second problem? That is, it's recognizable on this slide, but maybe not so obvious. There's a hint. It has to do with that line. It's an atomic, yes? What about it being an atomic causes problems? I thought atomic solved all our problems. Yeah, the assignment's going to be okay because both of those are going to be atomic assignments. So the assignment's going to be okay. The problem is that there's an atomic there at all. What do you mean? You're supposed to use atomics. So what's the problem? Why can't you just put one of these in a ring buffer? Well, there's this thing called implicit lifetime. We mapped this data. I'm a producer. I didn't create the queue. I didn't create it. I just memory mapped this thing. And I'm trying to tell the compiler that, hey, there's a queue there. No lifetime has ever been started. It's undefined behavior. Fortunately, here's an example just to describe to you the initial problem. Before 20, this was undefined behavior. After 20, objects can have implicit lifetimes, certain objects. The compiler is allowed to say, hey, this object, I'm going to assume its lifetime. But there's some restrictions. This is the exact example I gave you earlier. After 20, this is perfectly fine. Before 20, it's not. Well, it's not exactly true because we have time travel. But this is key. What is the compiler allowed to do with implicit lifetimes? Scalar types, implicit lifetime class types, array types, and CV qualified versions of these types are collectively called implicit lifetime types. All right? So what is an implicit lifetime type? A class is an implicit lifetime type if it is an aggregate or has at least one trivial eligible constructor. This, by the way, is not a trivial constructor, even though, and the reason is because it doesn't even compile. You're not allowed to say this. You can only default the special member functions. The only constructors that can ever be trivial are the default constructor, the copy constructor, and the move constructor. It would be awesome if a user could specify a trivial constructor, but you can't until Javier writes the paper. And it has to have a trivial non-deleted destructor. So, what's the problem? There's one place in the standard that talks about processes. One that I know of. And this is it. And it's in atomic lock-free. Hey, my atomics are lock-free. This should apply to me. The implementation should not depend on any per-process state. This restriction enables communication in memory that is mapped into a process more than once and by memory that is shared between two processes. Sounds exactly like what we're doing. We got memory mapped, shared between two processes, and I've put a stood atomic in there. Unfortunately, C++20 made this change. The default constructor used to be trivial. As of C++20, the default constructor must initialize a value. Sounds like a great thing, because now I've got values that are initialized, but it's no longer trivial. But wait a minute, Jody. You said any constructor that is trivial will do. They only changed the default constructor. This is a great time for a message from our sponsor. The greatest single C++ slide in history. Some people think it's archaic. Some people think it's outdated. I've had people tell me I need to stop showing that because nobody needs to know that anymore. So here's your pop quiz. What does this code do? Does it compile? Which, if any, of these static asserts will fail? If you are a professional programmer and you're unwilling to bet your paycheck on your answer, then you need to go back and look at that slide again. Because the bottom row is exactly that situation. There's a move assignment that has been user declared. Now, it's been user declared as deleted, but it's been user declared. So it's deleted, it doesn't exist. Which means that the move constructor is also not declared. The copy constructor and the copy assignment are both deleted. Why does that matter? Jody, you show that slide in every talk you make. Yep, there's reasons. Why does it matter? Look, this is what stood atomic was before 20. The copy constructor was deleted. That means there is no copy constructor. There is no move constructor. And the default constructor is no longer trivial. Stood atomic is not an implicit lifetime type. Because it's not an implicit lifetime type, how is the compiler ever supposed to know its lifetime? Well, how about if we call the magic, used to be called stood bless, now it's called stood start lifetime as. How about if we just call stood start lifetime as? Sounds great. Except you can only call stood start lifetime as on types that are implicit lifetime types, which stood atomic is not. So we have to create a size. We can wrap this with an atomic ref. The problem here is that now, if you ever use this as an atomic ref and as not an atomic ref, that's undefined behavior. And that really doesn't say what it does it? You kind of lost some stuff. So I've implemented my own atomic. The first go at this implementation was a raw implementation because the Apple Clang compiler didn't support atomic ref yet. As soon as Apple Clang supported atomic ref, I made my implementation be just atomic ref because it's much easier than trying to support the whole thing. If you want to implement your own atomics, you're in luck because Ben Sachs has a talk later today telling you how to implement your own atomics. But when you do, make sure that you don't make the constructor non-trivial. So messages must also be implicit lifetime. So any message you put into a shared memory queue has to be an implicit lifetime type. You go, oh, well, that kind of makes sense. Well, it's more than makes sense. In order for your program to have defined behavior, you really have to do this. We'll talk a little bit about cache line size. You saw that we were measuring things on cache line size. Really, this whole thing is I could use STUD hardware destructive interface size instead of using a macro, but I realized that Apple Clang was just wrong. On my Apple machine, I've got 128 byte L1 cache, so my cache line size is 128 bytes. But when I compile my code, it says that it's 64 bytes. Fortunately, I had a test that failed as soon as I upgraded to because Clang used to not support this. Apple Clang used to not support hardware destructive interface size. As soon as it did, my code started compiling with it, and then my tests failed because the cache line size was wrong. But if you look hard enough, you'll find mailing lists for both Clang and GCC, and they basically say, yeah, you really shouldn't use this in header files of libraries. Well, where else am I going to use it? But yeah, you really shouldn't. You shouldn't use it there because it's hard to get right, and it can change depending on your compiler flags. So my recommendation, if you're writing code like this, don't use, you might think, use hardware destructive interface size because that's the standard C++ way to do it. I'm telling you now, don't do that. So we're going to talk about the magic buffer. I'm going to go through this implementation. How many of you are familiar with this? The magic buffer? Only a handful. How many of you remember what I said earlier about it? Okay, so the magic, I don't know why it got called magic buffer. It's been around like forever. But the idea is that your machine has virtual memory, right? Your address space is all virtual. And all of the operations on your virtual memory map back to some physical page somewhere in your system. So, if you have a buffer, let's say you have 1 megabyte of a buffer, and you want to use it as a circular queue. If you use it as a circular queue, you have to keep extra variables and you have to do extra code to decide whether you've gotten to the end or not so that you can wrap. That is extra code and extra data that you don't need to keep track of. Let the operating system keep track of it. It's easier. It also can be faster, though you must, as everything that talks about performance, you must measure. But it can be faster as well. So if we have this 1 megabyte of data, this pink data, what we want to do is we want to get this 1 megabyte of data into an address space so that when I access that 1 megabyte plus 1 byte, the operating system itself will automatically reference the first byte. What does this allow me to do? It allows me to take any offset within my buffer. I mask off to the 1 meg, and no matter where it is, I've got 1 meg of contiguous memory at my disposal. I don't have to do any tricks. I can just access 1 meg, and it automatically will wrap for me. How do we do this? Well, in my implementation, I've got some arguments that basically I've got a mapping object that knows how to do it for Apple and for Linux. It also knows how to do it for non-anonymous data and anonymous, which is basically just in the virtual memory system, which on Apple you have to do very differently using their special APIs. But we're going to look at the mmap one to kind of explain how this works. So I've got this 1 megabyte of data. There's my arguments that I can pass in. I'm going to create 2 megabytes of anonymous memory. Okay, I'm going to tell the virtual memory system, hey, set aside 2 megabytes of data for me in the virtual system. It has not reserved any physical pages at all. It's just set aside 2 megabytes of virtual memory space. The next thing I'm going to do is I'm going to map my file, map my 1 meg over the first half of the buffer. I'm going to tell mmap, hey, I want you to map this thing, and here's the address I want you to map it to. And I know that address is good because I already reserved it as virtual memory. And so I map that 1 meg over the first half. Then what I do is I map that same 1 meg over the second half of data. And now what happens is that whole 2 megabytes of virtual memory, I go through the first meg, and as soon as I get to the next second meg, I'm automatically referencing that first meg of memory immediately. Everybody at least with me on this? And you can do this with memory in your system. It doesn't have to be memory backed by a file. It doesn't have to be memory in shared memory. You can do it with regular memory in your, like for things that are cross threads. This is kind of what that mapping call looks like. It's basically just a call to mmap. Figures out what's there, whether it needs to use shared, or whether it's anonymous or not. Do I have a volunteer in here? How close am I to actually having to cut off on time because of the video part? Or do I really, you guys are hot, right? You want me to get out of here? It says I only have 1 minute and 30 seconds. That's why I'm asking. Okay. So I'll try to get through some MCAS queues in the last few minutes here. MCAS queues, single producer, multi-consumer. Every consumer gets every message. The producer never blocks. Slow consumers may miss messages. It's up to them to recover if they can. At C++ on C, I talked about it. I won't talk about it here because I don't have time. But you can construct these queues, and if you looked at all that set of flags for my message queues, you saw where it could be single producer, single consumer, multi-producer. You can create one of these queues that is single producer, single consumer with one consumer, and then single producer, multi-consumer with all the rest of the consumers. And so what you could do is you could have one consumer that's pulling all the stuff and then archiving it somewhere. They will block if they have to. Normally they won't. And then you could have a recovery process where if somebody missed messages, he could ask somebody to replay those messages for him, right? So there's a way to do it without crashing. But I highly recommend David Gross's 2 talks, this one and this one. In the first one, he talks about seek lock multicast queues, which are basically with a seek lock. It's a type of lock that's used in the kernel a lot. This last one, he talks about what he calls fast queue, which is almost identical to the Daugaard queue we looked at earlier. And so we're going to look at an implementation, my implementation of a queue very similar. It's not his queue, but it's very, very, very similar. So let's look at the producer here. Before I waste the rest of the time doing this, let me first ask, because you can at least read the code on the things. Anybody got any questions? Nobody really interrupted me at all. Anybody got any questions?
Is the application demanding that you share memory between processes? What happens if you're across computers?
So what happens if you're across computers? It's a great question. So the way that the system works is that it knows by configuration what these queues are. So if you're across computers, you know what the queue you're supposed to talk to, an endpoint. If it's remote, depending on whether the system is configured to allow auto transfer or not, you would think you always want to have auto transfer. Why wouldn't you? But sometimes you might have a configuration wrong and you don't want to have an auto transfer. But if you have auto transfer enabled, it will recognize that the queue you want to talk to actually lives somewhere else. It will spin up a network communicator that will be a consumer of that queue, and it will come across and be a producer of a queue that you can then read on your own machine. Okay?
So the atomicity is maintained per operating system instance.
Correct. Correct. All right, so if we want to write, this is similar to what we've seen before, but this is actually how it's in the implementation, is that when we want to write, we get an instance of the writer. We give it some special information so it knows how to do some things. There's the writer that we construct, and we basically call our user and say, hey, here's the writer object, write some stuff. And then when it's done writing it, we call finish write. which cements that, right? All the stuff that it's doing writing does not touch any of the atomics. Okay, it's basically just going to prepare some stuff to write, and it's going to write into some stuff. And then when it's done, this finish write is where the atomics get updated so that the readers can see what's going on. And the reason this is there is because we're going to return what the user calls, and if they gave us, unfortunately, we still don't have a good pattern for this in C++. If they gave us a function that returns void, we just have to recognize it and not return anything. If they did give us something, we return what they've done. We call finish result, and then we return their value to them. This is basically the implementation of write span. If you give it a span, it will go get a buffer by calling prepare buffer. This prepare buffer is very, very similar to the prepare buffer or prepare write that we saw in the Daugaard queue, where it just goes off and says, hey, I want to get bytes. But instead of waiting for them, it just grabs however many it needs because it assumes that the readers are going to keep up. So it'll never, ever block. It'll always go get the number of bytes that it needs. And then it just mem copies that span of data, and then it updates its local counter. Remember, this writer has a local counter because the callback that I give you a writer, and you can write as many times as you want into it. And it's up to this thing to keep track. The only limit is you can't write more than one full buffer size in one callback, right? You're limited to that. So here's the one where we're just going to write any arbitrary data with a specific alignment. We do the same thing. We call this prepare buffer. We mem copy our data. And then we update our local counter. If we can do the same thing with in place, and this is repetitive by now, right? We prepare our buffer for how many bytes we need and the alignment. We call placement new inside of our data because no matter where we are, we know that we're always going to have contiguous bytes because we have this magic buffer if we have the magic flag on, which we will in here because it'll set it up. We update our local and we return. Our writer itself, the constructor of the writer, saves its current counter because in the destructor, it might need to revert it. Finish write, this is where it updates the shared memory to basically let the reader know that it's available. Our try read is similar, except in this case, there's only one way, right? Because we either read the bytes or we didn't, and we have to copy them. We can't give a view into the buffer because the writer might come around and write over it. So we have to basically make sure that we've got enough bytes. All right,